Hi everyone, this is Purnima Mahalingam and you're watching video lecture series on field theory. In previous class, we have seen what is boundary conditions for electric and magnetic field, and we have seen one of the boundary conditions for dielectric medium. And today we are going to see another type of dielectric mediums, the dielectric boundary conditions. And we are going to see is and two boundary. These are the things we have seen previously. Today, we are going to see the dielectric boundary conditions if the two mediums are different. How the conditions will be satisfied. Come, let's go to the video. Here, here we have a two medium, one and two. Here we have a two medium, medium one and medium two. These are the different mediums. Here we have a spherical. That is, previous we have this. We have the spherical change in surface and with help of change in height. So here with the height, for coming to height, change in height, what we are taking is we can also write as a del h for change by 2 and del h by 2 because this height is sharing with the both the surfaces. And there is a tangle and tangle and n vector, these two media. So we are going to find the boundary conditions for these two media. Here the dielectric boundary conditions d1n minus d12. What happens here? D1n minus D2n is equal to rho s. So D1n by D rho s days, the dn minus D2 is equal to rho s. If no free charges exist at the boundary, that rho s is equal to 0. That is D1n equal to D2n. That is D1n equal to D2n. The normal component of D vectors are equal to the boundaries. So Dn undergoes no changes on the boundaries and it is continuous across the boundaries. So D1n is equal to D2n and epsilon. This D we can replace as epsilon into E, the epsilon into E. So epsilon E1 divided by epsilon E2, that is epsilon. We can see E1 by E2, that we can replace like this. Then the normal component of D vector undergoes the same change across the boundary conditions. So Dn vector is said to be discontinuous across the boundaries. Okay. Here comes the dielectric boundary conditions of different mediums. Here we can see the different mediums. What happens with a particular angle? Here comes with an angle. Here a different media with comes with a particular angle. This is theta 1 with this with an angle theta 2. What happens here? We coming the dn1 d2 and we have an d1n. So we have two medium. This is what an dielectric boundary conditions with an angle. So that here we can represent the angle of sine theta, and on the cos theta we're getting the equations. So 1 divided by 2, what has happens? Equation 1 divided by equation 2, equation 1, equation 1 divided by equation 2, sine theta 1 divided by cos theta. 5 minutes கழிச்சு வாங்க. 5 ஒரு 10 minutes கழிச்சு வாங்க. Next here we are taking this E1 and last. We have seen this is last. What happens here it is, sorry, equation 1 and equation 2 divided, that is sine by cos, that is equal to tan, that is sine theta 1 by tan theta 2 and epsilon 1 by epsilon 2 and epsilon 1 epsilon naught into epsilon r, the tan theta 1, this we can be replacing. This is called as law of reflection. Okay. Now, the conduction of dielectric boundaries are the boundary conditions and conductors. If the two mediums are conductor, one is dielectric air condition air and one is a conductor in any media conductor. One is dielectric material, one is in a conductor. This is an air, we can consider this an air. Here in a conductor, we can represent this in epsilon. Here we can represent this into epsilon E. Okay. So this is in dielectric, this is an epsilon E. Okay. Now, here, what are the dielectric boundary conditions? So, this is the square spherical form, and that is in a spherical form. What happens here? We have a dielectric air. Here we have conductor. That is whatever maybe the conductor U vector is equal to 0. And the conductor, the dielectric boundary conditions, whatever things we are having, whatever things we are having, we are taking this, the interface between the perfect conductors and dielectric shows in the figure. The applying the equations, the path ABCD shows the figure. So the path ABCD, even in this medium or in this spherical or in this whatever the medium it is, what happens is finally it shows 0. The boundary conditions for the normal components are obtained by applying Gauss law on a small pillbox shaped volume as given the figure. So assuming here the white H change in height is equal to 0. Here what happens? So rho of yes, finally the rho of yes. Okay. The conductor in free space. So what happens here in this free space? What happens? Dielectric boundary conditions for free space. No electric field exists instead of perfect conductor. So external electric field, if any, is normal to the conducting surface as given by dN is equal to rho s. dN is equal to rho s. The conductor free space boundary conditions. In free space, this is a special case of conducting dielectric conductions, and this is obtained by replacing epsilon r equal to 1. Then the equation, what happens is converts like this: dN is equal to epsilon naught into epsilon r En, that is 1. That is epsilon replacing epsilon r equal to 1. Then the equation becomes like this. As in the earlier class, dt, that is triangle of d, is equal to epsilon naught into epsilon r, that is et, that is equal to 0. So we can have in two conditions, whether it is a 0 or it isn't rho s. So this is what in free space conducting boundary. That's both. We are next is about free space conductor and conductor, and we have seen that what happens, that a magnetic boundary condition. Here we can see the medium 1 and medium 2. Here we can see the medium 1 and medium 2 with an angle. There is medium 1, there is mu1, medium 2 is a mu2. What is this? A B, there's a B1, B2, BT2, this BT1, and a BN2, BN1. What about the surface is? The height is divided del H and del by 2. And the area, what happened area? That is a line. And there's a change in surface. This here with a change in surface. Here the magnetic flux in surface 2, there's a magnetic flux in surface 1. Okay, this is what the boundary conditions for the two media. The magnetic boundary conditions consider the boundary between the two isotropic homogeneous linear material with permeability mu1 and mu2. At the boundaries, the magnetic flux density may be decomposed in the normal component of Bn and the tangent component of Bt. Applying Gauss law for the magnetic field on a small pillbox shapes volume, what happens? B vector into d is equal to 0. So B vector, it is change in surface. B vector change in surface in medium 1 and medium 2 is equal to 0. So Bn1 is mu1 is the magnetic flux density in the first surface 1 and surface 2. Okay, so that is equal to surface 1, surface 2 is equal to 0. So magnetic field surface 2 minus surface 1 with respect to normal component is equal to 0. So the normal component of B vector is continue across the boundary between the two adjustment media. This is what the boundary conditions. And finally, boundary condition B2 minus N is equal to 0. Finally, the answer is 0. This is what the magnetic boundary conditions B2 minus B1 is B2 minus B1 is equal to finally with the angle cos angle is equal to 0. And this B can write as mu and mu into H, and we are replacing this. We are getting this equation. The normal component of magnetic field intensity are not continuous across the cross boundary. The normal component becomes continuous only when mu1 equal to mu2, and in case there is no boundary between two material. So this is what the pictures. So this we can see in next class. Thank you so much for watching this video.